Hello everyone, welcome back to ptet.chemistry channel. In this video, I'll cover a theory called valence shell electron pair repulsion theory. So it's a theory developed many years ago. I forgot when exactly, but it will allow you to predict shape and bond angle of molecules. So this is an important concept in covering AS level chemistry usually, because where would you encounter it eventually? You encounter it eventually when you think about redox. You might not have thought about it before, but yes, you do need to think about redox. More commonly, you will see it in organic chemistry when they link it with hybridization, when they link it with a concept of change in bond angle, whether you're doing polymerization or whether you're going via intermediate or etc. etc. Where else will you see valence shell electron pair repulsion theory? I guess the redox bit is probably under inorganic chemistry, where we are going to justify, is it a redox reaction or is it not a redox reaction? And believe me, there's actually manifestation of VSEPR in there, okay? So a lot of people, when I say people, it says students, and I've seen a lot of lessons online as well, they rely on this idea of counting bond pair. Okay, that's basically bonding pair of electrons or pairs of bonding electrons versus lone pair of electron. Okay, so when we talk about lone pair, we are referring to non-bonding electron. Non-bonding electron. The bond pair refer to bonding electrons. Okay, so it's important to get our terminology correct. And VSEPR is applied to covalent bond. So we don't talk about VSEPR when we talk about ionic bonding, or when we talk about metallic bonding, because you cannot count metallic bonding, you cannot count ionic bonding, because those are non-directional. Because covalent bond, well, why did I put it in an inverted comma? I don't know why. The reason we can apply VSEPR to covalent bond is because they are countable. And you know that covalent bond is directional. So we talk about sigma bond and we talk about pi bond, okay? So those are directional. So sigma bond is formed from head-on overlap of orbitals, whereas a pi bond is formed as a result of sideway overlap of orbitals, which I'm sure you have covered in your school lesson. Okay, when we talk about a bonding pair of electrons, okay, so there are two ways of looking at it. Yeah, so in VSEPR, when you counting bonding pair of electrons, you only count the sigma. Okay, that's the thing. A lot of people, when you have double bond, for example, so what am I talking about? When you have carbon-carbon double bond, so that is 1 sigma 1 pi, or you could see me writing 1 sigma 1 pi like that. Okay, so both represent the same thing. It's a double bond. There are two covalent bonds, of which one must be sigma and one must be pi. So that is only counted as one bond pair. Okay, but how many bonding electrons are there? Okay, now this is the confusing thing. So in that CC double bond, okay, there are 4 shared electrons, okay, because you have one covalent bond, which is 2 electrons being shared between the 2 carbon. You have 2 covalent bonds, that means you have 4 electrons being shared in this double bond. Similarly, like if I have triple bond like that, there will be 1 sigma plus 2 pi. That would be altogether 6 electrons shared in that triple bond. Of course, you know that carbon usually will form 4 bonds and there will be other electrons around, but I'm specifically talking about within that triple bond, yeah? But within that triple bond, you have 1 sigma, and you don't have more than 1 sigma because of how they overlap, which is head-on. So if we have 2 sigma, it has to be in the other direction rather than in between the two same atoms. So it has to be on the other side and on the other side. It cannot be between the two atoms. You have 2 sigma, right? Because of repulsion. As a result of how sigma bonds are formed, you're going to get quite a tremendous repulsion if you form 2 sigma, yeah? That's why you form 2 pi, which is from the sideway overlap of the remaining orbitals. So what happened then is because we identify the sigma, therefore we will say that is contribute to 1 bond pair, okay, in the context of VSEPR. So I think this is what a lot of students struggle with, because it's quite confusing, isn't it? It's quite counterintuitive, like what do we constitute as a bond pair, what do we constitute as a lone pair. It's just that in the context of VSEPR, when you count the bond pair and the lone pairs are easy to identify because they are not involved in bonding. But the bond pair here refers to only the number of sigma bond. Okay, it's probably easier if I start by talking about some examples. Yeah, I'll have another video where I talk specifically on hybridization. I might cover a little bit of hybridization in this video, so depending on time and context. All right, so we started out from so we're gonna have a little bit of what we call chemistry vocabulary. Okay, in the sense that it's about knowing a few known examples, which would be whatever is stated in your syllabus, and applying them to unfamiliar situation. Okay, things like CO2. I have drawn display formula rather than dot and cross, or you could call this as some sort of Lewis formula. Some people would know it as Lewis formula, where instead of showing dot and cross for the electrons, we will use line. Each line represents 2 electrons because each line represents 2 covalent bonds. Okay, so there's 2 electrons being shared, and each line is 1 covalent bond. So 2 lines would mean 2 covalent bond. Altogether around carbon there are 1, 2, 3, 4. So the carbon form 4 covalent bond. It will have no charge. The oxygen typically form 2 covalent bond. That's because it shares 2 of its 6 valence electron for bonding. So in doing that, it would have 6 electrons of its own plus 2 more from the other atoms that share their electrons to itself. Then both of them will get the noble gas configuration. Okay, so when we count bond pair, this is what we do. We look at the central atom. Okay, so around the carbon, what do you have? You have 1 sigma plus 1 pi. You have 1 sigma plus 1 pi. We just want the sigma for our bond pair. Okay, so the number of bond pair or bonding pair of electrons, okay, as you would call it. I might just call it bond pair from now onwards, so it's just 2. Okay, we are talking about a pair, all right? So we have 2 sigma bond, 2 sigma covalent bond. Okay, so there are 2 bond pair of electrons in the context of VSEPR. Okay, of course, covalent bond, there are 4 covalent bond altogether, but we only count the sigma when we want to work out the number of bond pair. And the number of lone pair of electrons is going to be 0 around the carbon, because carbon is a group 14 element, or you would call it a group 4, well, depending on your periodic table, whether you have it as the Roman numeric, okay, or this numerical value. So they will have 4 outer shell electrons, or I will call them 4 valence electrons. It used 1, 2, 3, 4 for bonding. It used all of them for bonding, and that's why you have none left, 0. So altogether, we need to think about this idea called VSEPR, valence shell electron pair repulsion. Valence shell, outermost shell, we're just talking about outermost shell, electron pair repulsion is to do with the electron pair repulsion. Okay, so there's a general rule in VSEPR that says when you have no lone pairs, then the bond pair will repel equally. The 2 bond pairs will repel equally because you have no lone pair, only because you have no lone pair. So you gotta state the number of bond pair, the number of lone pair, and when the number of lone pair is 0, then you know the bond pair will repel equally. And when they repel equally, you in this orientation, we only got 2 groups that repel equally. the two groups being the oxygen in one way and the oxygen in the other way, you are going to get linear 180 degree. What happens then if we start to increase the number of bond pair but still maintaining the number of lone pair being 0? So we are still going to talk about equal repulsion, things like BF3 or even BCl3, or instead of BCl3 you can think about AlCl3, which is actually the catalyst used in electrophilic substitution reaction in benzene chemistry. Okay, or you can think about other things which are similar. So what are we looking at? We're looking at a group 13, or you call it group 3, whatever, 3 valence electrons. I know the display formula as such because 3 outer shell electron used up for bonding. There is no lone pair. Okay, each of these is a covalent bond. It's formed with a group 17 element which will share 1 electron in the outer shell. You will have seen it in things like HCl or HF. They always form single covalent bond by sharing the 1 outer shell electrons, and they'll form 1 single covalent bond there. You can even think of it as BH3 like that as well. Yeah, there's no harm in it, except that in BH3 there's no lone pair around the hydrogen because it uses the 1 and only electrons for covalent bonding. In fluorine, it will have 1, 2, 3, 4, 5, 6 on each of the fluorine. Okay, because the fluorine only uses 1 of the 7 outer shell electrons for bonding. Anyway, we are going to count the number of bond pair. Okay, so that's nice and easy there because you get 3. So because I have different examples here, I'm going to talk about around the central atom. Okay, so the shape is always about the central atom. I forgot there's one good example I could have shown you, which is actually in your GCSE or your O-level case study. I'm sure you know SO3 molecule, yeah, from your contact process when you do the equilibrium between SO2 and oxygen. This is a good example because, well, sulfur is a group 16. Okay, sulfur is group 16. Sorry, 16 is Vi. There's group 6. I could use this number, which is 16. And then that means it has 6 outer shell electrons. We will not associate it with this usually, right? But because these are all double bond, so it uses 1, 2, 3, 4, 5, 6. It uses all 6 of its outer shell electron for bonding. It has no lone pair. So we can think about the number of lone pair in all of these cases. It's dependent on the group number, yeah? And the display formula you draw has to be consistent with it as well. There's 0 lone pair because it uses all the 6 outer shell electron for bonding. It uses all the 3 outer shell electron for bonding. Okay. How about the number of bond pair? So for the AlCO3 and the BF3, they are straightforward. For this one, it's not so straightforward. But based on what we know about VSEPR, a double bond is 1 sigma and 1 pi. Okay, so it has 1 sigma and 1 pi. So in SO3 molecule altogether, you have 3 sigma and 3 pi bond. But we are just interested in the number of sigma bond. So it's just 3 bond pair because only 3 sigma bond. And guess what? No lone pair and 3 bond pair. The 3 bond pair of electrons repel equally. This is again using valence shell electron pair repulsion, which means you got to talk about electron pair repulsion theory after you work out the number of bond pair and lone pair. Okay, just now you have 2 bond pair that repel equally and they will give you the linear and 180 degree. Here you get the 3 bond pair that repel equally and they will give you a trigonal planar, because if you think about in the plane of this screen or the paper, you get 3 groups that want to stay away apart equally as much as possible. That's going to give you like a 360 degree, which is 1 whole revolution divided into 3 slices of the cake, which is 120 degree. So it's called trigonal planar. As you can see, it's planar. It's in the shape of this screen or the paper. Okay, it's flat. It's 120 degree here, 120 degree here, and 120 degree here because they repel equally. Then you ask the question, what if it's not BF3? What if it is BF2Cl? Well, if it is BF2Cl, this is still a group 17. This is still going to be single bond, which means it's still going to be 1 sigma, 1 sigma, 1 sigma. This is still going to be a group 13 element with H used up all the 3 outer shell electron for bonding. which means you also still have 0 lone pair. So the same concept apply, the same shape, the same bond angle, despite you having changed it 1 fluorine to 1 chlorine in a normal substitution reaction. Okay, so the concept really comes down to work out the number of bond pair, work out the number of lone pair, whatever examples you are given, relate it to whatever basic examples you know, knowing that bond pair in the context of VSEPR refer only to the sigma bond. Okay, so now we're going to go to the next more complicated example, which is actually 4 bond pair and 0 lone pair. Okay, so your VSEPR will say 4 bond pair of electron and 0 lone pair of electrons. So what am I looking at? Okay, I'm looking at this exactly. This is a carbon. Okay, this is a carbon which has 4 outer shell electrons. It uses 1, 2, 3, 4 for bonding. I have drawn it in this case because it will make sense from the shape later on. Okay, that they will repel equally. So the 4 bonding pair repel equally. Well, repel equally. So you can write down the same argument in full. You are going to get tetrahedral 109 degree. The question really is, why can't they be planar? Well, if they are planar, if you say they are planar, then you will say 360 divided by 4, which is 90 degree. So you want to maximize the repulsion, right? They repel equally. When the electrons repel, because these are electrons in the sigma bond, you want them to repel equally. You want it to spread apart as much as possible. When you are planar, you are 2-dimensional. In the 2-dimensional, you have the 360 degree, divided by 4, you get 90 degree. Guess what? Atoms occupy space. That's the most important thing in organic chemistry. Things are not 2-dimensional, it's 3-dimensional. There's another dimension you can enter, which is coming out towards you and going away from you. Okay, so there's a 3-dimensional axis, and that means for them to repel equally and for them to stay apart as much as possible, there's an alternative. I can adopt tetrahedral, which is not 90 degree. 109 degree is bigger than 90 degree. The bond pair, which consists the sigma bonding electrons, they are further apart than when they are 90 degree. How does tetrahedral looks like in 3-dimensional? So I'm going to do my best to draw this 3-dimensional thing. Imagine when you have a cuboid, when you have a carbon in the middle, so one of the hydrogen will be there, and one of the hydrogen will be there, like that, and then the other hydrogen will be here, the other hydrogen will be here, like that. So when you look from the top, okay, or when you look in the plane of this, these two are going to be flat, but one of them is coming out towards you. So this is coming out towards you. We draw them as wedges like that. That is pointing at you right in the eye. These two are flat in the screen or the paper. This is pointing away from you, okay? So that's what we call tetrahedral, 109 degree. I know it as 109 degree. I know some books will have put it down as 109.5 degree. That's entirely fine as well. So 109 degree, 109.5 degree. It's really up to you which one you prefer. To be honest, I don't think there's much difference. Coming to the end of it, VSEPR is a prediction. Okay, there's going to be some differences in reality. Okay, so this is how we draw 3-dimensional tetrahedral, because it is not flat like that. Okay, unlike in your GCSE or your O-level. To show the tetrahedral shape, you have to show the 3-dimensional stuff. It's too flat, and you cannot draw. What you cannot do is you cannot do things like this. So that doesn't work, yeah, because that is not showing the tetrahedral shape at all. That's incorrect, even though you show one out, one in. Okay. Another common mistake that people do would be they draw things like this. Oh, they're like, I have 2 in the plane and then 2 out of the plane. Technically speaking, this doesn't quite work as well as this. What you could do, however, is you could draw the other way around, which is like the mirror image, and you would think about mirror image when you talk more about optical isomerism in an organic chemistry context. So this is the same as that. You could draw like this because the 2 bonds that are in the plane of this paper, they are like that. Okay, they are next to one another. Not only that is 109, this is 109 degree, that is also 109 degree, that is also 109 degree, or you could use 109.5. okay, SiCl4 is an important example, as you will see the chlorides of group 14 as chlorides of this period 3 element silicon is actually in most A-level syllabus. I'll show you something even cooler, MnO4 minus. So a lot of students will have heard of MnO4 minus being manganate 7, but we have never really taught it in school before, and this is now time for you to think about it. MnO4 minus is an ion, but within the ion itself, you have covalent bond. Yes, you do have covalent bond. But between the Na plus or K plus or whatever, you have ionic bond between the ions, but within the ion itself, you have covalent bond. The Mn there is Mn plus 7, okay? If you go back to your electronic configuration of manganese, is going to be argon, 4s2, 3d5. Outer shell electrons used for bonding. Strange, right? Outer shell electron used for bonding. It's got 7 outer shell electrons. 1, 2, 3, 4, 5, 6, 7. No lone pair. Why 4 bond pair? Well, the oxygen likes to form double bond, except that in this case, it will have a negative charge. That's why it doesn't form double bond. Guess what? There is going to be 1 sigma plus 1 pi, 1 sigma plus 1 pi, 1 sigma plus 1 pi, 1 sigma there. 4 sigma means 4 bond pair of electrons in the context of VSEPR with no lone pair. That is going to be tetrahedral and 109 degree. So I've just shown you that you can apply VSEPR not just to molecules, but to ions that consist of covalent bond within as well. Going back to trigonal planar, there's something else you need to know as well. When you have carbonate, so you have heard of carbonate anion, and that's very important anion because you will do group 2 carbonate, which is a big case study in energetics as well as group 2 chemistry. And you have heard about carbonate in your test for acid. Carbonate reacts with acid, right, to give you CO2. So it's CO3 2 minus. So why is it so special? Again, just like the manganate 7 anion, what you have is you have ions, okay, but within the ion itself you have covalent bond. The carbon is a group 14 element, just like that. So it has 4 outer shell electrons, 1, 2, 3, 4. Use all that for bonding. You have 0 lone pair of electron, okay? So you need to define this, yeah? I'm just using an acronym because I'm getting sick of writing lone pair, yeah? The bond pair is, we count the sigma. So this is a sigma, 1 sigma plus 1 pi. So you need to be very careful, okay? You don't count the pi when you count the bond pair for VSEPR. There is another sigma, there's another sigma. So altogether you have 1, 2, 3. You have 3 sigma, so 3 bond pair. So altogether, you have that, the 3 bond pair of electron repel equally. What you are going to get is, you are going to get this as 120 degree. Okay, so I hope that makes sense there. I can keep on going. In your O-level or GCSE, you have done alkene chemistry. Alkene chemistry. Why did I draw alkene chemistry like that? Because this carbon is a carbon-carbon double bond, is 1 sigma plus 1 pi. We are looking at one particular carbon. You see, bond angle or the shape is at one particular central atom. You can either be here or here. Shape here is one thing. Shape here is another thing. So you need to define them individually. I'm going to look at here. So there is 1 sigma, 2 sigma, 3 sigma around this carbon. This carbon has used 1, 2, 3, 4 for bonding, okay, including 1 for the pi bond. So it's going to be 3 bond pair repel equally around this carbon with 0 lone pair. Therefore, trigonal planar, 120 degree. I'll talk more about this in the hybridization topic. That is your alkene chemistry. Very, very important. This is your alkane chemistry. Alkane chemistry, which is your CnH2n plus 2. Your organic chemistry will talk about carbon being saturated. So all the carbon bonds are single bonded. So the carbon will naturally form single bond to hydrogen. But when you have saturated hydrocarbon like that, we draw it like that, but we know technically it's not correct now because in 3-dimensional, technically it will look like that. So if you're asked to draw 3-dimensional, it has to be three-dimensional. But in reality, when we do mechanism or when we do organic chemistry, we just draw them as lines like what I drew earlier, because it's so much easier to represent. And the geometry itself is implicit in the sense that you know the carbon, when you form 4 covalent bond, there's 4 sigma around each carbon. 1, 2, 3, 4 around this carbon. 4 bond pair of electrons. 0 lone pair of electron because it uses 1, 2, 3, 4 for bonding. The 4 bond pair of electron repel equally. You're going to get tetrahedral. You are going to get tetrahedral geometry. Geometry is tetrahedral. The bond angle is 109 degree or 109.5 degree around that carbon. Okay, so I'm just going to cover this off and cap this off with the idea of 5 bond pair of electrons and 0 lone pair of electrons. Okay, in reality, when you have 5 bond pair of electrons and 0 lone pair of electrons, you can do a couple of things. Okay, but in the context of A level, they simplify it to only one geometry that you need to know, which is essentially the trigonal planar geometry. So imagine the trigonal planar, which is your number of bond pair, number of lone pair. This was earlier, right? And then you have your linear. You have your linear geometry, which was 2 bond pair and 0 lone pair. Then imagine that you could add both of these together. Okay, if you add both of these together, what are you going to get? You are going to get like that. So the bolded one is coming towards you. The flat one are in the screen of the paper. This is going away from you. So we have a central atom bonded to 5 substituents, okay? Where if I add them together, like combination, linear combination of both, I'm going to have 5 bond pair and 0 lone pair. That is when the bond pair and the lone pair repel equally. Therefore, the 5 bond pair repel equally. And you can immediately see that previously you have that as 120 degree. This is your trigonal planar. This was your linear with 180 degree. Now in this combination, bond angle is between atom, atom, and atom. So about the central atom, there are actually 2 different bond angles. That is 90 degree, which means that is also 90 degree because remember this was linear. Okay, so it's still 90 degree bisecting them apart. So this is between the vertical and the equatorial. Okay, whereas in between the equatorial and the equatorial is 120 degree. And this is a shape that we call trigonal bipyramidal. It's like you have a pyramid. Okay, so your central atom is there, and then you have your connecting 5 substituent 1, 2, 3, 4, 5 trigonal bipyramidal. It's like a linear combination of these 2 geometry which you've seen earlier. All right, so you see this in things like PCl5, PF5, SbCl5. Obviously these are your case study. I'm just extending it to group 15 pentahalide. Penta because there are 5, and then group 15 because it could be any elements in the group 15 or group 5 that has 5 halogen associated with it. Okay, so the very last case study example that is very simple involve the number of bond pair and the number of lone pair being 6 and 0. That means the 6 bond pair will repel equally, and that will give you something known as square planar. Oops, sorry, not square planar. It will give you something known as octahedral. Okay, what do we mean by that? Things like sulfur. Okay, things like sulfur, when it's bonded to 6 fluorine, okay, it will adopt this geometry where I have 2 of the, what am I doing? SF6? Doesn't matter. It's the same whether it's SF6 or SCl6 because each of these will be a covalent bond. They are all sigma, 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 sigma. So you have 6 sigma, therefore 6 pi. Each of the SF is a sigma bond. So 6 bond pair, and then 0 lone pair. And then you can talk about this thing where they are 90 degree So this is 90 degree. This to this is 90 degree. This to this is 90 degree. This to this is also 90 degree. All of them are 90 degree. So even that is 90 degree as well. Okay, so they're all 90 degree. They repel equally. Okay, so these are the few examples where they are really simple, where the bond pair simply repel equally, because there are no lone pairs in these kind of structures where you could count them, right? Okay, so I'll leave it there for this first part of VSEPR. In the next video, I will discuss the implication of presence of lone pair and how would that affect the shape and bond angle in further examples and application of VSEPR. So if you like this video, please subscribe to the channel, and that's if you like my teaching style and explanation. Not sure if it's helpful to you, and if you think it's helpful, then spread it among friends and teachers and colleagues, and yeah, thank you for watching.